In this video, we're going to consider this problem. This platform ABC is supported by this wire that has a diameter of 5 millimeters. And the wire is made from A36 steel. Man is sitting on the seat at C and determine the normal stress and the elongation of this wire. So we're going to consider this problem. And first of all, we might as well do some geometry here. You can see that this is a 600 millimeters, 800 millimeters. I'm going to put this into meters. You can work with millimeters if you like. I'll change these to meters, though. I like working with meters a little bit better. So then that means that this length right here is going to be the square root of 0.6 squared plus 0.8 squared. And actually that comes out to 1 meter. And then it would be good to find this angle here. You could either work with the angles or you could work with like the ratios of the sides here. On this one, I'll work with the angles. So the angle of theta here, the tangent of theta is going to be the opposite over the adjacent, or the arctangent of the opposite over the adjacent, like that. And then this comes out to about 36.9 degrees. For this angle here. And so we have everything we need here. So probably want to make a free body diagram of this beam right here. Again, remember the free body diagram, you only put the reactions and any loads or that you might have. So like over here, we'll maybe have like a AY here. And maybe an AX here. We're going to end up summing about A, so we actually won't even need to find these. We'll put them in. Then over here we have, this is about 0.8 meters. And we have this coming up like this, and this was 36.9 degrees. And this is 0.6 meters. We have this load here. The man weighs 80 kilograms. We're going to change that to newtons, of course. Like here. And that's our free body diagram. And we should give this a name. This is going to be from our wire here. We'll call this F DB, maybe. Like that. And this is what we're going to need to find, is the stress in our wire. So that's our free body diagram. And then we'll sum the moments about A to find out what this is here. And that's going to be our FDB. And then let's see if we're going, this force is going to be counterclockwise, so I'll be positive. And then that's going to be FDB sine, or 36.9 degrees, times the moment arm, 0.8 meters. And then this going down here in the clockwise direction, minus 7, 84.8 newtons, times this distance here from A to there, that's 1.5, 1.4 meters. Set that all equal to 0. Then if we solve for this FDB, put that all in your calculator, you get something around 2287 newtons. And to find the stress in our wire, the normal stress is going to be like our force in the wire, which is going to be this FDB, divided by the area of the wire. That's going to be 2287 newtons, divided by the area. And we're given that the diameter is 0.5 millimeters. And 0.25 pi times the diameter of the wire squared. And if you put that on your calculator, you get like 116 times 10 to the 6 Newton per meter squared. And that's our stress. And we should check, you can check in the back of the book that this is less than the yield stress of the material. And so we're good to use our normal equations then. So again, this is going to be the normal stress. That's the answer to this part here. And then next we want to find the elongation. Or deflection. And remember that equation is delta is equal to the force. Sometimes they call it P. And I'll call it P in this case here, PL over AE. Again, P is going to be, in our case, the force in the wire, which was this up here. And then L will be the length of the wire, which was 1 meter. The area of the wire was this right here, 0.25 pi 0.005 squared. And then our E is going to be our Young's modulus, which in the back of the book tells us that that was 200 times 10 to the 9th. That's going to be Newton meters squared. And of course, this was meters over here squared. And so when you put that on your calculator, you'll get an elongation of 0.00584 meters. And that's the answer to the problem.